This video we're going to be talking about logarithms within the Maxima algebra series, and so we're going to start by looking at this document. Logarithms. This idea developed around the 1600s in order to facilitate multiplications, divisions, and powers. Somebody had the idea that if you take the number b, which we're going to call the base of the logarithm, raised to a certain value y, and I give you x, then y becomes the logarithm of base b of that number x. Okay, so let's solve for y using Maxima. Well, Maxima says, okay, well, you have to calculate something that I call the log of x and divide by the log of b. I need to let you know that log is the only logarithmic function available in Maxima. That corresponds to what is called the natural logarithm. The natural logarithm is something that we're going to see more in the calculus subject, but it's a logarithm that comes out naturally when you expand a series. And in many other literature references, you're going to see it as ln of x, I mean the natural logarithm of x. And because nowadays the notation log of x, or previously, sorry, that log of x represented the logarithm of base 10. Why base 10? Because our numeric system is base 10. But in Maxima, keep in mind that log means a natural logarithm, and any other logarithm will have to be calculated somewhat like this. The base of the natural logarithms is the constant e, sometimes called the Euler constant, which is the number 271, 82, and so on. It's an infinitely long, non-necessarily repeating irrational number, and that represents that quantity. Now, I'm going to use a generic notation here to define the logarithm of base b. And I'm going to say if b to the y is equal to x, then y is equal to the log base b of x. Now, this cannot be written in Maxima. All right, so in order to be able to write some sort of logarithm of base b, I'm going to define a function that I'm going to call uppercase log of variable x of base b. And following this idea, it turns out that the logarithm of value of x of base b is equal to the float of the natural log of x over the natural log of b. So I'm going to define that function. For example, 2 to the 5th is equal to 32, so if I take the log 32 of base 2, I get 5. However, this is going to be like a quick idea of how computers store numbers. It turns out that Maxima uses what is called a single precision numbers, whereas many other software use a double precision. With single precision, you can get things like this. The logarithm of 64 over 2 should be 6, but in reality it comes out to be 59999. We know that in the end 5999999 is equal to 6. But the reason is that here you have an integer number 62 and an integer number 2, and somewhere in the calculation the integer is stored in a certain way that when you get the logarithm it gives you 599. But it turns out that if you write 64.0 and 2.0, these are called floating point numbers because they have a point, they have a decimal point, it sort of floats around. And when you do that using the log function of base 2, you get the exact value. So something to keep in mind, and don't get discouraged by it. If you get 599, it basically means 6. So to calculate logarithm of any base, you can use this function, log of xb. And for example, logarithm of 1000 base 10, logarithm of 10 base 10, of 2 base 10, sorry, logarithm of 10 base 2, logarithm of 256 base 2, logarithm of 256 base 4. Those values correspond to 3. This is the logarithm base 10 of 2. This is the logarithm of base 2 of 10. That means 2 to the 3.32 gives you 10. 2 to the 8 gives you 256. 2 to the 4 gives you 4 to the 4, sorry, gives you 256. So y equal log of x base b implies x equal b to the y. Check in the case log 2 of 10, 10 to the previous result should be giving me 2. log 10 of 2 raised to the value 2 giving me 2. So that's sort of like this exponentiation is the inverse function of the logarithm. Commonly used logarithm system. I mentioned the natural logarithm, and this is the one that Maxima prefers. It's more natural in a sense. In the past, logarithms of base 10 were heavily used because of the fact that our numbering system is base 10. So we can define a log 10, a logarithm of base 10 by this function, and see, we find that the logarithm of 1000 is 3, of 100 is 2, of 2 is 0.3810. General properties of logarithms. Okay. What comes up here is a series of rules for logarithms, and I don't want to spend time just reading them. So if you want, you could pause the video right here and read them, or you can also read them, pausing the video, you can read them from the document that you should be able to download from the YouTube channel, and read about these rules, and then we'll come back to them. Okay, so basically it says logarithm cannot be a negative. Negative numbers don't have logarithms. Logarithm of the base is equal to 1. The logarithm of 1 is base 0. Numbers that are greater than 1 have positive logarithm. Numbers smaller than 1 have negative logarithm. And the logarithm of 0 doesn't exist. Logarithm of a product is equal to the sum of the logarithm of the terms. The logarithm of division is equal to the subtraction of the logarithm of the dividing over the divisor. The logarithm of a power, a to the n, is the n multiplied with the log of a. Logarithm of the root, which is a power, is dividing by that root.